Okay, so hello. Thanks a lot for the introduction. And as Enrico mentioned, I'm just finishing my PhD at University of Lausanne. And one of my main research interests was causal discovery from observational data. I found this topic quite interesting, and especially from machine learning perspective, there are many methods that are already implemented in R, which I would like to briefly present to you today. Okay, maybe I go in presentation mode. So I will start with an example, which I find quite interesting because it's one of the first things that I saw when I started the PhD. I think we all know the story that storks deliver babies, which of course it's not true, but we keep seeing it everywhere. It's in many cultures. We see it on postcards. This is what we tell to the kids and so on. And one professor decided to actually do a study on this. And what he found out was that if we take into account the number of storks per countries and the birth rate, there's actually quite a significant correlation. So the p-value is very low. But of course, if we try to recommend a policy to the government, we would not be able to say that if we want higher natality, we should bring more storks. So the thing is that, as we know, we should not imply correlation from causation from correlation. And there is this principle by Reinbach, which is saying that if we see a correlation between two variables, it might be due to one of these four cases. So either we have a causal relationship, so X is causing Y, or an anti-causal relationship, maybe Y is causing X. The third case is that maybe there is an unobserved confounding variable, which is actually affecting both X and Y. And this is why we actually see the correlation, which in this case would be spurious correlation, or it might be due to selection bias, as in the fourth case. So what happened with the storks and the babies is that actually we were not taking into account the areas per country, which is basically the hidden confounder, which is causing both the number of storks and and also the number of births per country. So this is one way where we might actually take into account causality and causal features as better predictors. So this is something that we would like to learn from, that basically if we build our models mostly with causal features, we would be able to have better predictions and maybe better interpretability of our results. So before doing this talk, I did a search on Metacran, and I actually saw that there are quite a lot of causal packages already. However, I can briefly categorize them in three groups. So the first one, which is the biggest one, is actually mostly related to economics methods. So mostly measuring the causal effect of treatment and control variables, mediation and so on. The other group is basically mostly for multivariable cases. So when we're trying to build a causal graph, which is very similar to Bayesian network. And the third group, which is the most recent one, and it's also quite a hot topic in the machine learning research for the moment, is the invariant causal prediction. However, in this case, this means that we need data from multiple environments. So basically we have some causal relation, some data that we're interested in, but we have, for example, the same data for multiple countries. So this is also an assumption that we would need if we want to apply this method. So in today's talk, I will focus on something that seems much simpler, which is taking into account only two variable cases. But this is already challenging because every time that we have three or more variables, the way to discover causal relationships is doing conditional independence tests. And when we have only two variables, we cannot really do that. So this is why it's a more challenging case. And also, I will focus only on observational data. So we don't have randomized data, we don't have interventions, we don't have multiple environments. All we have is two variables, X and Y, and we will try to discover which one is the cause and which one is the effect. So I'm a bit more oriented towards machine learning, but I think that, all of these methods in causality, I know that they're applied and they come from economics, from stats and so on. So I think that it's important for all of us to know them. And also many of these papers are actually implemented in R. So I think it's nice for this community to know about them as well. Just a quick overview of what I will talk about is first I will introduce one of the point views for causal discovery, which is based on compression or causal discovery by stochastic complexity. And I will present three methods which are based on the same postulate: the information geometric causal discovery approach, slope, and quantile-based causal discovery. And I will conclude with some results from experiments that we did. So this is just to put it in a bit more formal way, where we consider that we have two variables, cause and effect, such that it can be presented in a functional model. So the cause is just a variable that comes from a noise source, and the effect is a function. It's presented in a functional form as a function of the cause and another noise variable which is independent of the cause. So these two variables are independent. And how we present this in a graphical model would be that we have an arrow from the parent to the child, or an arrow from the cause to the effect. So one way to discover causal, to get causal discovery from the data is if we find a way to discover some asymmetries in the data. Basically we know that if we have this joint distribution of x and y, there are two valid ways to decompose it. So it can be either the marginal multiplied by the conditional, so x multiplied by the conditional of y given x, or the other way around. And what this postulate says is that in the causal direction, the factorization will have a shorter description. So what we mean by shorter description is in terms of Kolmogorov complexity, which is just the number of bits, so zeros and one, that we need to describe the rule that generates x. So we have a program that generates variable x. So how do we describe this program in terms of zeros and ones? So the intuition is that in the causal direction, this complexity will be smaller. So basically the joint distribution will be factorized in a shorter description. So, and this is what we will try to discover from the data. The problem here is that Kolmogorov complexity itself is not computable. So we need to find a method which is more practical, and it can be also related to some statistical criteria. The most simple thing that we can do is that we can assume that there is an additive noise. So y is just a function of x and some noise variable. And we know that the noise variable is independent of the cause. So to test this in data, what we can do is first fit a regression model in one direction. So we first fit the conditional of y given x, and then we test for the independence of the residuals that we get with this function and the variable that we assume is the cause. And then we do the same in the other direction. And then we just compare the p-values of the independence tests, which will give us the most probable causal direction. In R, this is also very simple to do. So we fit a nonlinear regression in one direction, we get the residuals. Here we use a kernel embeddings test for the independence between the cause and the residuals, and we do the same in the other direction. And we see that the p-values are quite different. So this is one way how we can discover causality. This is just the visualization. So this is the functional model from the previous slide. So it's X on the, so it's a cubic model. And we see that in the causal direction, the errors are independent from the cause, while if we try to fit the anti-causal model, there is still some structure in the data. So and this is how we are able to see the asymmetry. However, what if we want to avoid the additive noise assumption, because this can be quite restrictive? Then one of the first methods that was doing this was the information geometric causal inference. In this case, there is no model assumption for also not for the additive noise. Basically, we will rely on measuring entropies to get the complexities of the distribution. And this method will assume that there is a deterministic causal relation. So there is no noise. And the information geometry interpretation comes from the fact that we can compute complexities of the distribution with regards to some reference measure. And this is quite an important point for this method, because the reference measure, as suggested by the authors, are uniform or Gaussian. And this has an implication on the results of the method, as we'll see. So it's only 3 steps method. So for some observational pairs, we first have to normalize them to the reference measure of choice. So we either make them 0, 1 uniform, or we make them standard Gaussian, so 0, 1 unit variance. So that is the first step. We do the normalization, and then we calculate the entropies of each distribution, because we consider them to be the projection with regards to the reference distribution. So this is a standard entropy estimator that can be applied. And then from this course, we compare which one is the lowest, and that one will be the true causal direction. It's also very simple to implement it in R. First, we have the function for normalization, then we have the entropy estimator, and then we just compare the scores to get the true causal direction. So this is quite straightforward, and it's very scalable to large data sets, and it gives quite good results in practice. However, what if we want to actually have the noise in the data and allow for more flexibility? Another way to compute Kolmogorov complexity is if we can rely on the minimum description length. So this has been developed in the 80s, and it's just a method that decomposes the complexity of a given model and a data in 2 parts. So first we encode the description of the model, and then we also encode the residuals or the data given this model. The intuition here is that with the model, with the length of the model, we represent the compressible part of the data. And with the length of the data given the model, we represent the noise in the data. So this is just a practical version of measuring the Kolmogorov complexity on both sides. So we will just measure the MDL for the same inequality. It's just that now we have a practical version how to do that. So we have 4 summons that we 4 summons on each side. So we need to compute the code lengths for the marginals and the code lengths of the conditionals to be able to discover the causal direction. And one of the first methods which is relying on this is the slope method by a group from the Max Planck Institute in Saarland University. And what they do is, because we need to calculate the code length for the models, this means that these models need to be parametric. So they choose either linear, quadratic, cubic. So they're trying to find the best fit for the regression model for the conditionals. And then for the residuals, that they assume that they're Gaussian. So they can compute the log likelihood, which is an equivalent of the code length for the conditionals. And what they do, a similar thing that they do as IJCI is that they encode the marginals with a uniform prior. So I'm not showing the code for this one because it's a bit larger. So, but everything is available online and it's in R and it's really easy to use. So the authors made available their whole repo. But the limitation of this method is that really we are restricted only to this group of functions. And we also assume Gaussian distribution. So in practice, this is not always the best choice. So another step further is, what if we try to avoid the parametric functional models and the assumptions about the noise? A natural choice would be to do quantile regression. And this is a method that I was working on together with Thibaut Vater and my supervisor, Valérie Chavez. So in this method, we again rely on the MDL principle. It's just that this time, instead of doing the linear, quadratic, any parametric kind of regression, we use non-parametric methods for regression, and we also use quantile scoring to get the residuals. So we don't assume any kind of distribution, which actually helps us to be able to capture not just the additive noise model, but also multiplicative noise models or location scale models. So in the MDL equation, this is what we do. So we replace all the models with quantile estimators, and we compute the residuals or the code lengths using quantile scoring. Actually, this helps us, as I said, to make the method more flexible because we don't make any assumptions about the functional forms or the distributions. And also, we compute at least 3 quantile levels, and we aggregate the results from multiple quantile levels, which makes the method a bit more robust. So if there are some regions where there's less data, or maybe it's a non-symmetric or skewed distribution, our method should be more robust in these cases as well. So in experiments, so when we try to discover cause from effect, if we just plot the 2 variables, so just pairwise plots, we cannot really visually distinguish. So this is synthetic data. The headings at each plot are the actual causal directions, but we can see that it's quite indistinguishable. So these are different cases of additive noise, of heteroscedastic noise. Also, we tried different models where the functional models will be injective or non-injective, which also makes it a bit more difficult for some methods. And this is a benchmark of real-world cause-effect pairs. So in this case, we see that, yeah, actually the data can be non-linear, injective, non-injective, that there is additive noise or maybe heteroscedasticity and so on. So we compared different methods across all benchmarks. And for the quantile causal discovery, as I mentioned, we pulled the results across multiple quantile levels. So each M here is how many quantiles we actually used. So in the first case, if we use only 1 quantile, we see that this is not enough. So these are all the different benchmarks. Sorry, I didn't mention, it's all the different benchmarks. And we're measuring the accuracy. So how many correct causal decisions we made and how many times we were wrong. So just with 1 quantile, we're not really able to discover, especially in the multiplicative noise. It's not really enough. If we use multiple quantiles, the methods are already doing well. IGCI, as I mentioned, it's quite important which reference measure we will use. So if we use the uniform reference measure, the method is not doing so well because most of the synthetic data case, the synthetic benchmarks are with Gaussian noise. So the choice of reference measure is quite important. And slope, the issue with this one was just because it's normalizing the data to 0, 1 because they use the uniform prior. But on real data, it was really beating everyone. And however, I want to mention that the authors of this algorithm this year developed a new version, an upgraded version, which is called Sloppy. It's also implemented in R, and it's doing well across all benchmark. They again rely on the MDL principle, but now they use the BIC score to compute the parameters of the model. So this was all I have to say. I just want to again say that the causal discovery can really improve our model predictions and can also help us when interpreting the results of our models. That causal discovery is also available for observational data, not just for interventional data or randomized experiments. We also have many methods in R. And also the 2 variable cases are really easy to extend to multivariate case because we can just estimate a graphical, we can just estimate the graph as a skeleton and then orient each of the edges 1 by 1. And it's also a very hot topic in machine learning at the moment. So I think that we should all keep an eye on the new tools that are coming up. And thanks for your time.
Okay, great. Thank you very much, Natasha. So we have time for some questions. So let me check. Yeah, so here we have a question. Do you have some examples comparing your methodology with DAG-based causal methods?
With DAG-based, so in our paper, we do compare, so our method, it's for 2 variable cases, so it's not really straightforward, so it's extendable to DAGs, but we use, for example, the PC algorithm to estimate the skeleton, and then we orient the edges in the skeleton using our method. And in the paper, yes, we compare against different DAG methods, and it was competitive. So I think it's not beating state of the art, but it's competitive.
Okay, maybe you could remind us what is DAG exactly. So it's an acronym.
Directed acyclic graph.
Okay.
So yeah, it's the multivariate version of causal discovery, the multivariable causal discovery method.
Okay. Thank you. There is also here another question. So your talk is about discovering causal effects without running an experiment. So the person who's asking, Arben, he was wondering if you have made cool discoveries by using these methods.
So we were mostly focused on developing the method, and I think that so I didn't really. In causal discovery, it's very controversial because usually we need domain experts to tell us if it's really a causal relationship or not. Mm-hmm. So I can apply the method to different datasets, but I'm not the one to say if it's like really an interesting discovery or not. So I think that people from other areas should try to use these things.
Mm-hmm. Are you planning, or have you already planned to work with domain experts and to apply the methods that you presented with them?
So not for the moment, but we had, so at conferences and presentations, we have questions from groups that work on climate and different like areas like ecology. Yeah. So I think that the method can and will be applied there. So we will see some results on how this is going.
Yeah, I think I heard about that. Okay. Then there was a question about your slides. So yes, all the slides of today's conference will be available, and I think there will be a link, or there will be a communication on the website of the SatRday conference. I think the link was already provided, but it will surely be available on the website.
Okay.
Enrico, I think the question was more about the code.
The code. So I didn't put the references here, but I didn't put the links to the code, but I put the references to the papers, and in each paper there is a link to the code. So I can either summarize all the links if it's better, or I don't know, whatever it's easier.
We can also talk about this in the room. Maybe Audrey, you can speak directly to Natasha as well. Yeah.
Okay, I think no, there is no additional questions. So thank you again, Natasha. So if there are other questions, as I just said, there will be rooms where you will be able to ask them directly to Natasha.